Hi everybody, this is the lecture on the first part of chapter 2, which is on predicate logic. So a predicate is a statement with one or more variable entries. The predicate itself is neither true nor false, until we somehow know something about the variable entry. On the variable entry or entries. So for example, P of x would be, say, x is a pony. All right, I mean, that's true or false until we know something about x. P of P of 7, right? 7 is a pony. Right, is false. We could also have a predicate say something like this. G of x is the statement x bigger than 7, in which case g of 7 is true, or bigger than 3. And g of 3 is false. You could also have two variable predicates. Right? S x y is equal to x plus y equals 10. Right? So S for 6 is true, whereas S03 is false. Okay, so predicates, statements with variable entries. Now, other than just plugging in values for the variables to give some sort of truth to statements that use predicates, for the variable entries in predicates, okay, one can also quantify the variables over some domain of values. Okay, so there's two types of quantification. Two types of quantification that we use in predicate logic, and they are as follows. There's universal quantification, and universal quantification goes like this. If we write like this, upside down A means for all x, P of x means for all x, P of x is true. Right? Or something like, every x makes P of x true. Each x makes P of x true. Or no x makes P of x false. All right, that's another way to say it. Okay, so universal quantification. Formally, given a domain D, which is a set of values from which x is drawn, okay, we say that for all x, P of x is true when P of D is true for all little d in the domain. So any domain element that you choose, when you plug it into P of x, it gives you a true statement. So for example, let's take the following statement. For all x, x is bigger than 0. Okay, so that's a statement, quantified universally. For all x, x is bigger than 0. Let's look at a few different domains. We'll say domain is the set of positive integers, like that. Well, is it true for every x in the domain, x is bigger than 0? Yeah, 1 is bigger than 0, 2 is bigger than 0, 3 is bigger than 0, 4 is bigger than 0. It's all true. What about the domain -3, -2, -1, 0, 1, 2, 3, so on and so forth? Is it true here? Well, no, certainly it's false here. Or the domain equal to 0, 1, 2, 3, 4, so on and so forth. Well, even though it is true for every element in the domain that for every element x in the domain, x is bigger than 0. 1 is bigger than 0, 2 is bigger than 0, 3 is bigger than 0, 4, 5, 6, they're all bigger than 0. There's one guy where it fails. 0 is not bigger than 0. Okay, and in predicate logic, when we mean for all x, we mean exactly that, for every x. So just being wrong on being false on one x makes the whole thing false. For every x means for every x. Oh, excuse me. All right. So that's universal quantification. Existential quantification. So there exists x, P of x, and that's a backwards E, means there's some x making P of x true. All right, or there exists an x, say it that way, such that P of x is true, or some x's make P of x true. Specifically, formally, there exists x, p of x is true over domain D when there is at least one element, little d, in the domain such that P of D is true. There exists at least one. At least one, again, means at least one. Just means could be one. Could be two, could be three, could be infinitely many, could be all of them. At least one means at least one. Okay, not anything else. So, for example, let's go back to this same kind of thing here. There exists x such that x is less than 0. So there exists x such that x is bigger than 0. Here, is there at least one thing which makes x bigger than 0? Yeah, there is. There's at least one. Okay, in fact, all of them, every x in here has x bigger than 0, but that doesn't matter. At least one means at least one or more. Exactly that. There exists an x such that x is bigger than 0. True. There exists an x such that x is bigger than 0. True. There exists an x such that x is less than 0. There's nothing in here. When an existential statement is false, when everything fails in the domain, it fails to satisfy the predicate. Nothing in the domain satisfies the predicate. Right? What is the negation of there is? The negation of there is means there isn't. So if I asked you, the statement, there is a horse in the room. Well, again, these statements don't work as well remotely, but okay, I'm in my office here. And I said the statement, there is a horse in this room. The negation of there is a horse in this room means every item in this room is not a horse. Every item in the room is not a horse. So, any rate, here, there exists an x such that x is less than 0. False. Nothing. Fails for everything. Here, well, there's few things, well, infinitely many things that are less than 0. Here, nothing. 0 is not less than 0, so it's false. The statement fails everywhere in the domain, or the predicate fails everywhere in the domain. So, existential quantification and universal quantification. Stacking quantifiers So if you want to stack quantifiers like this, it means the following. For every x, there exists y, pxy, and you have a predicate dealing with x and y, or a predicate logic statement dealing with x and y, is true over domain D when for any x in D, there is some y that goes along with x to make p of xy true. There is some y, and that y depends on x. So for every x, there exists a partner y for x such that p of xy is true. So, for example, something like that. Over the integers, the domain consisting of all negatives, whole numbers, 0, and the positive whole numbers. So over the domain of the integers, for every x, there exists a y such that x plus y equals 0 is true. Is true. For any x that is chosen, right, y equal to minus x exists in D, and x plus y is equal to 0. Right, so if I pick x equal to 5, then the y that I'm looking for is negative 5. If x is equal to 20, then the y that I'm looking for is negative 20. For every x, there exists a y going along with x that satisfies the predicate statement. X plus y is equal to 0. When you switch them around, it means something different. There exists x such that for every y, pxy means, okay, for every x, sorry, there is an x in the domain. There's one particular x. For every y in the domain. Makes p of xy true. Right, so again, going back to this statement here, over domain D, there exists x such that for all y is false. There exists an x such that for every y, x plus y is equal to 0. There is not one x to which you can add to any y and get 0, right? I mean, the x plus y is 0 if and only if x is equal to the negative of y. Okay, and there's nothing that cancels everything additively. This is true. There exists an x such that for every y, x plus y, or x times y, equals 0. This one is true. There does exist an x. Is true. Let x equal 0, right? And 0 times y equals 0 for all y in the domain. Right, so for multiplication, 0 times anything is 0. But for addition, there's no, there's no special element that adds to y with every other element to get to 0. Okay. So for all x, there exists y. There exists y for all x. Here's an example I like to give sometime. It's not exactly predicate logic, but let's listen to it for a moment just to kind of get the feel. For every student at Wright State, there exists a name by which he is called. Every student at Wright State has a name by which he is called. Right? So your name is Fred, her name is Elizabeth, my name is Daniel, or student or employee. For every, person at Wright State, there exists a name by which he is called. Okay, so now let's change around the order of that quantifier. There exists a name such that every person at Wright State is called by. Well, it sounds false, because there's not one name that everybody is called. Not everyone's name is Daniel, right? Not everybody's name is Cynthia, not everybody's name is Fred. But it is true, but for, in a different sense, right? There does exist a name, one single name, that every student or every person at Wright State is called by. That name is Raider, right? We like to call ourselves the Wright State Raiders. So the name Raider applies to every student at Wright State. So that's true too, but in a very different sense. So like this is all for one and one for all, right? This is one for all. There is one for all. Or no, sorry, all for one. All are for one, right? All are for one. Everybody is for one thing. Right? That's this one, all for one. Even though it's sort of the other way around. All for one and one for all. And this would be one for all. So I'll leave you to think about that. All right. Let's talk about translating English language statements into predicate logic. English language statements into predicate logic. So consider some large domain. So some domain that is sort of bigger than what you tend to be talking about. Okay, so oftentimes in this kind of exercise, we take D to be the whole universe and everything in it. So for example, let D be equal to the entire universe and everything in it. Both real and imagined. Whenever you want to universally, so it's two main principles in doing these translations. Whenever universally quantifying a subset of the domain identified by P of X, write the following. For all X, P of X implies. For example, well, let's do the second principle, then we'll go over examples. Two, whenever existentially quantifying over a subset of the domain identified by P of X, write the following. There exists X, P of X, and something. Okay? And within both of these principles, okay, so I'm saying universal quantification goes with implication statements. Existential quantification goes with conjunction statements. It's never the other way around. Never write for every X, P of X, and. Okay, this is always false. Here, never write there exists X, P of X implies something. This is always true. Whenever you are writing an English language statement, whenever you're saying a statement of some sort, making some sort of claim, it's always in some way controversial. You know, the truth, the verity, the truthfulness or the falsity of what you're talking about is always kind of in question in some way. So you would never write something that's vacuously false or vacuously true. Okay, so I mean, you wouldn't write you wouldn't write a statement that was vacuously false or vacuously true. So let's take some examples so we know what we're saying here. Give some more illustration. I know it's sort of disgustingly abstract what I'm saying so far, but it'll be clearer now after some examples. Example: P of X is a pony. G of X is X eats grass. R of X is X runs fast. B of X is round. Okay. All ponies. Oh, and the domain is the entire universe. And everything in it. Both real and imagined. All ponies run fast. Or all ponies eat grass. All ponies eat grass. Okay, for all X, G of X. For all X eats grass. Is that it? No, that's not it. This is false. Absolutely true, it's false. In the whole universe and everything in it. For all X, everything in the universe, it eats grass. Okay, I don't eat grass. Okay, my table, my desk here, doesn't eat grass. You know, the planet Jupiter doesn't eat grass. Whatever it might be. Okay, it's not everything in the universe eats grass. X eats grass. For every X in the universe, X eats grass. That's not what we're trying to say. We're trying to say all ponies eat grass. So we're just talking about ponies, not talking about anything else. What you write is we're universally quantifying over a subset of the domain. That subset of the universe being ponies. Okay, so for everything in that subset, for all ponies in the universe, if it's a pony, then it eats grass. That's what we're trying to say. All right. If this statement is true, then this statement is true. If this statement is false, then this statement is false. They have the same truth value. Okay, for everything in the universe. So suppose it is true. Suppose it is true that every pony in the universe eats grass. Okay? Pick an X in the universe. Pick X in the universe. So I pick a pony. I picked my pony, my little pony. Okay, so X is My Little Pony. Some X chosen from the universe. My Little Pony is a pony, right? And My Little Pony does eat grass. So that's a true statement. Okay, suppose I pick another X in the universe. I let X be my desk here. X is my desk. So my desk is a pony. False. It's not a pony. So this is true. I don't care if it eats grass or not. When the hypothesis is false, okay, the implication is true. All right, false or true, doesn't matter. Okay, irregardless of the conclusion. So this is true. For every X in this statement is true for every X in the domain. For every X in the universe, this is true. If it's a pony, then it does eat grass. If it's not a pony, don't care. If it's an elephant or a cow or at my desk or a Jeep or whatever, whether it eats grass or not, the statement is true. All right? All right. Suppose this is false. Suppose not all ponies eat grass, okay? I have a pony. And we refuse to feed it grass. We only feed it oats or whatever. So all ponies eat grass. That's false, okay? Because there exists one pony in the universe, my pony. We just feed that pony oats and alfalfa. So it's a pony, true, but it doesn't eat grass. Or at least it's not fed grass, so that makes the statement false. So it's not, when you say all ponies eat grass, to make it false, all you got to do is show me one pony that doesn't eat grass. Okay. All ponies are brown. All ponies are brown. Same kind of statement for every X. X is a pony implies X is brown. All right, same kind of thing. For every X in the universe, if X is a pony, then it's brown. If it's not a pony, we don't care. Okay, well, suppose this was true. That for some reason all ponies in whatever universe we're living in, they just happen to be brown for some weird reason. Okay, so all ponies are brown. So then, if that were true, then this would be true. Because for any X in the universe I pick, when it's a pony, it's got to be brown. Because this is some weird alternate universe where you only have brown ponies. Okay, if it's false, like in the universe we live in, well, I got a pony, but it's white. Or it's black. Okay, so it would be a pony, but it's not brown. So that statement would be false. Okay, so here's the kind of the joke that I wanted to say, and why I'm talking about ponies. When I want to say to you all ponies are brown, the way you negate an existential statement, not negate, the way you display an existential statement to be false is to give one example, okay? One example where it's not true. So when I say to you all ponies are brown, right, you would say that's a false statement by showing me, the proverbial horse of a different color, right? Well, that's a horse of a different color, so the statement is false. All right. No ponies eat grass. No ponies eat grass. What does no ponies eat grass? Say it without the no. Say it as all ponies. Right? Take the no out of the subject. Right? The subject of the sentence. We're saying no ponies eat grass, so I'm somehow, making the negative in the subject. All ponies, what? Don't eat grass. Right? It means the same thing. No ponies eat grass. All ponies don't eat grass. For every X in the universe, if X is a pony, then it does not eat grass. Or you could think of it that way, another way, no ponies eats grass. Another way to think of this is as follows. to translate the statement. Would be, not translate, to rewrite, I guess. All ponies eat grass. All grass eaters aren't ponies. Right? This says if it's a pony, it doesn't eat grass. The contrapositive of that is if it's a grass eater, then it's not a pony. All right, so that's the contrapositive statement. All right, how about existential? Some ponies are brown. Oh, let's go back up to that thing about don't write for every x, p of x, and. Never write for every x is a pony, and. Such a statement is always false over a large domain, the whole universe. Right? For every x in the universe, x is a pony and, something. Don't care what. It's always false. Not everything in the universe is a pony. And I don't care what you're saying otherwise. Or not otherwise, what you're saying in addition to that. Right? For every x is a pony and x eats grass or something. Obviously false, because not everything in the domain is p of x. Not everything is part of that subset when you're talking about. So never universally quantify and then put conjunction. Universally quantify your subject and then put a conjunction. It's always universally quantifying your subject, implication. All right. So next statement, some ponies are brown. So this is existential quantification. Some ponies are brown. There exists x, p of x, and b of x. There exists x such that x is a pony and x is brown. Right? There exists a pony that's brown. Right? So I have a pony. My pony, it's out in the stable in the back, and that pony is brown. So that's one pony in the domain. That's one x in the domain of the whole universe. That's a pony, and it's brown. Right? Or if, this statement was false, we just don't call ponies brown. We call them, what's another name for brown? We call them dun, right? We don't say brown. We say dun if it's brownish in color. So, for every, how do you display an existential statement to be false? An existential statement is displayed to be false, okay, by saying that everything in the domain doesn't satisfy what you're talking about. Every element in the domain does not satisfy. So, for everything in the universe that you picked, right, either it isn't a pony or it's not brown. Right? Everything does not satisfy that. So if you wanted to say something like the following. Why am I drawing a blank here? Some ponies speak English. Some ponies speak English, right? That would be, some ponies speak English. That would be false because, right, for every x that you pick in the universe, either that x is not a pony or that x does not speak English. If you had a pony, well, ponies don't talk, so it doesn't speak English, right? So everything in the universe doesn't satisfy what we're talking about. Okay, some ponies are brown. What else? Not all ponies are brown. Not all. Not all. Not all is there exists. The negation of all is there exists. Right? Not everybody likes chocolate. Not everybody likes chocolate. I mean, somebody out there doesn't like chocolate. Right? Not all ponies are brown. Means there exists X, such that X is a pony, and X is not brown. Okay, how long have we got here? We're at 40 minutes. Okay, so let's end the first part of the lecture here, and we'll have the second part of the lecture later.